Testing 1, 2, test podium. Handheld 2. Test 1, question, test 1, test 2. Test 1. Test 1, test microphone 1, handheld 1. Test 1, lab 1, lab 1, lab 1. Who wants the handheld? Who wants the handheld mics? They're muted right now.
Okay. But they're on?
They're on. Yeah, these are the ones that I have. Not the ones that, there's a box that Paula gives you. Yeah. So I'm just using the ones I have today.
So is this what I wear? Rather than wear something,
It's completely up to you. I'm not going to force you to wear this. If you want it, it's available. If you don't, if you're comfortable at the podium.
when the questions start, I'll put it on maybe.
Okay. I will leave it here, but I will...
With my advancing age, my hearing isn't as good as it once was. And sometimes it's hard to hear questions. So I may need you or someone to translate the question.
Laura's going to be up here.
Okay.
She's going to start up that part, so she can maybe help you with
I will
that.
come.
I'm going to be running around with the microphone.
I'll come down and make sure this is on.
Unmute these with this?
No, I mute them. I've got a control board. That's with the iPad.
So they're all good to go. They'll stay.
I've got extra batteries if something happens, but that should be more than enough
Okay.
for this event.
Great.
I'll come down and get this on in the question time since it doesn't have to be.
Oh, so put it on at that time.
I think that's what he wants.
Okay.
If you can convince him to put it on now, then call it something. The vlog is great.
Okay.
That was the
But you can probably just discreetly do it while we
Yeah,
start.
I could just put it on and put it in his pocket. If you can convince him to do it now, we can make it disappear and kind of look a little better, but he just wants to put it on in question time.
Okay, let me just check again. And then I'll sort of cut it off for the final question around 5 to 7.
Sounds good.
Okay. And John, also, he's wondering if he could put the mic on you now. He can kind of hide it. It'll keep you from having to do it later. And then, we'll have to. So we're good.
And then I'll just use the mic on the stand.
Yeah.
And Dick will as well.
Yeah. Good. And did I introduce you to Adrian?
No.
Let me do that.
Is she here?
Yes.
Is it okay if I put this on?
Maybe
right here.
Right here?
Yep. Let me see.
Or
Actually,
the other
other
way.
side.
Maybe
Go
it
ahead and
should
put
go
it
on this side, yeah.
Or I can flip it.
Well, let me.
Put that in the pocket?
When she sits down.
Oh, actually, I'm going to take this off, probably.
Okay.
Let's do it on the shirt.
Okay. You can do that. Let me flip it.
Flip it, yeah. If it gets hot, I'm going to take this off.
Yeah. Okay. And I will mute it until the question time. Do you want to run the cable down your shirt, or do you want to be visible? Doesn't matter to me.
I'll make it visible.
Okay.
Is that about right?
That's fine. Yeah, that's great. And then just put that in your pocket, or on your belt. And like I said, it's muted, so you put it where you want it. All right, I'm just gonna
And then we can tuck this in.
Yep.
Yeah.
Is that going to stay?
I should. If you want to clean, if you want me to clean it up a little bit, I can.
Yeah, let me. I'm going to
I
put
can
this
tape
inside
it,
the
yeah.
shirt.
Okay. I can also tape it.
Yeah,
Okay.
this will be fine.
And then when you're ready, are you starting or is there somebody going to announce you?
No,
It's muted on my.
somebody else is going to
Okay.
introduce me.
I just need to make
Yeah.
contact with him so I can see. if
Sounds good.
Everything is muted.
Yeah.
Right now. So.
Sounds good. Hi, how are you? Good to see you.
Good to see you. That idea, the big brand talk, man. Running it, yeah. Cool.
Yeah.
Yeah. Great title for this thing. So, philosophy, yeah. Nice to see you, man.
Good to see you. Hi, Nancy. Glad you could make it. Hi. Hi.
Hey, how you doing?
Good.
Ask people to take their seats, so we'll start in just a couple of minutes.
Yeah.
Come on, Nancy.
The what?
My wife is here, but she's not.
She's out there. Yeah.
Good evening,
Where should I
everyone.
sit?
If you could please
Right
take
here?
your seats, we'll get started in just a couple of minutes. If you could please take your seats. Thank you.
Are you going to sit here when I get up? Okay. No, it's okay. I'm going to be good. You're fine.
John, one last thing, because you're being bombarded right now.
Is-
Is I have these signs that I will put up if you like, that just let you know. You can.
Well, let's see. Six.
and
Don't bother,
you
because
can-
I
you
will
can
watch the clock.
Totally ignore it if you
Yeah, yeah. The last question is the only important one.
want. Okay.
Yeah,
Okay.
Um,
then I will leave it to you to manage.
that sounds good.
I forgot your water.
When?
Alice is grabbing it. Ready?
Oh yeah, is there? I'm ready.
Yes.
Is
Alice
there water?
grabbing the water. So
Okay.
I'll just flip it up there.
Yeah, good.
Sorry about that. You ready, Megan? Just about ready.
What?
Cute little flowers.
I know.
Are those from Rumble?
I know. They do a little bit. I think Megan brought them from somewhere.
Megan, do we start Berkeley time or do we start at 5:30? I just asked you to take it. Well, I mean, I can start. I have a few. Once I start saying something.
How you doing?
Good.
Good.
Having fun with all this. I guess we're about to have a lot of fun with all this.
Yeah,
This activity.
the Saturday and Sunday events are going to be really
Yeah.
great. Yeah. Are you guys going to be able to make the panel?
I hope so. At least
Yeah.
part of Saturday.
Yeah.
Dick's event was really fun.
Yeah.
It was so great to see the errands of students.
Yeah.
I'm sure you have many.
You remember Philippe Martin? With the tie? Yeah.
Welcome, everyone. Good
Yeah.
evening.
He came all the way from Brussels. What? Yeah, that's right. Yeah.
Welcome, welcome.
Hey there.
Good to see you.
Good to see you.
Is this on?
How you feeling?
Just another
Wistful?
talk.
Wistful?
No, not at all.
Thank you, Jen. Welcome, everyone, to the 24th Annual Energy and Resources Group Lecture on Energy and the Environment.
We are honored to have as our speaker this evening Energy and Resources Group and Environmental Science Policy and Management Professor John Harte. In a moment, ERG Emeritus Professor Dick Norgard will be introducing John, but before I hand the microphone over to Dick, I just wanted to make a couple of announcements. So first and most important, I wanted to extend a thank you to Adrienne Roth, who is here tonight, and her family and friends who, through their annual donations to ERG and to the Roth Fund, have made ERG's annual lecture possible. So thank you so much for your contributions. On behalf of ERG, I also wanted to thank everyone here tonight who donated this past year to ERG's Big Give recently. These gifts are going directly to very much needed student support. And I wanted to point out that if you feel inspired to give to ERG while you're here, even on your phone, there's a link on the back of the program. If you missed your opportunity during Big Give, it's not too late. So now please join me in welcoming Dick Norgard, who will introduce John.
I'm pleased to have the honor of introducing our speaker this evening. Professor John Harte is one of the many Sputnik generation physicists who went interdisciplinary with the environmental movement that started in the latter 1960s. John graduated from Harvard in 1961, earned his PhD in physics from Wisconsin in 1965, and spent the next 8 years doing theoretical physics at the European Organization for Nuclear Research in Switzerland as a professor at Yale University and at Lawrence Berkeley National Laboratory. During the 1970s, however, his passion for nature suppressed his curiosity for theoretical physics, and his mind wandered to environmental systems and how they could be better understood, managed, and respected. And this led to his transition onto the faculty of the Energy and Resources Group. Many Sputnik generation physicists who went interdisciplinary bent their minds and careers to nuclear policy and then science policy more broadly. John Harte took a different path. It is not that he ignored policy, but he bent his physics-trained mind to biology and ecology first, and then his research findings led to novel policy insights. John Harte and his students were among the first to argue and document that ecological feedbacks are critically important in climate change. Physical scientists and engineers dominate climate science policy, and we as a society, still do not seem to realize that we have a very fragile biosphere at risk and in need of delicate care on a massive scale. John's passion for nature has driven him to ask basic questions about organisms, ecological communities, and ecosystems. Spanning biological scales is not common within ecology, and John's work with his students has made important contributions at all these scales. His recent work has focused on developing theory that explicitly links these scales to understand how, for example, metabolism of individuals relates to numbers of species in a biome. John develops a general theory and then tests it with cleverly designed experiments and observations, which in turn leads him to deepen and broaden the theory. Importantly, he's not afraid to start simply. This combination has benefited enormously from his summers at the Rocky Mountain Biological Laboratory, where thinking and observing nature up close are a day-to-day pursuit, uninterrupted by many distractions of modern life. This evening's lecture, titled The Quest for Simplicity on the Other Side of Complexity, promises to be a great example of this mode of John's work. John.
Thank you, Dick, for a lovely introduction. I want to begin with a few quotes about simplicity from, among others, some of my favorite quoters. One that the title comes from is from Justice Oliver Wendell Holmes. And I'll let you just read it. It's a short quote, and it is where the title of my talk came from. But at the same time, I want to, if he's here, or even if he's not here, thank Eric Berlow, who brought my attention a few years ago to this marvelous quote. The second quote by Antoine de Saint-Exupéry, the author of The Little Prince, is especially pertinent to preparing this talk. I found over and over again as I prepared the talk that I had to heed these wise words. Otherwise, it would be a 3-hour talk instead of a 1 hour. Finally, of course, Winston Churchill, who came up with brilliant quotes about just about everything, even had something to say about complexity and simplicity. And my last quote is, of course, from Albert Einstein. And in a way, it's a nudge. It's a word of warning about looking too hard for simplicity. Don't look beyond what's reasonable, and we'll see as the talk progresses how his words are relevant. But to begin, I want to just mention the relevance of the picture at the bottom of the frame. Einstein knew much more than I did when I was 6 years old about the conservation of angular momentum and the additivity of momentum vectors. If I had known what he knows, I would not have burst out crying at the end of World War II when my dad told me he was going to give me a bicycle for my birthday. And the reason I burst out crying was I couldn't conceive of a two-wheel bike standing upright. It would tip over. And I had happily ridden my tricycle all over the Bronx where I grew up, but not a bicycle. So what did he do? My dad took me, we were sitting on a park bench in the Bronx at a little park, and I was explaining my fear of riding a bicycle. And he said, well, look, he took a quarter out of his pocket and he put it on a hard surface, and of course the quarter fell over. And I got even more angry and upset and said, look, see, it can't work. But then, clever man, he rolled the quarter on its edge, and of course it stayed upright. And that simple illustration actually reassured me, and it stuck with me for the rest of my life. So the power of a simple model. I want you to just draw your attention to what I'm holding here in my hand. It's the back of an envelope. That's the original envelope. That's where it all came from. Okay, so a subsequent step came when I was merrily doing elementary particle theory at Yale University, where I was on the physics faculty in 1969. And I got invited to take part in a National Academy of Sciences study of environmental problems in the Everglades. The organizers, one of whom was Murray Gell-Mann, also a birder, knew that I was a birder and thought I'd enjoy doing something to help try to save the Everglades. The issue was that there was a proposal to drain the Big Cypress Swamp in order to build a huge airport in which we could land the supersonic passenger planes that we were projecting to build to match the Concorde that the British and the French built. We never built the plane, it turned out, but before that plane was canceled, there were plans to build supersized jetports, and the only sensible place to build it in Florida, which would be the terminus for South American flights, was in the Big Cypress Swamp, right at the northern edge of the Everglades. And it would have diverted the flow of water to the Everglades, and we were quite convinced it would have destroyed Everglades National Park. So we studied and studied and studied the problem, and we learned all about the ecology of South Florida and the hydrology, the land, the geology, the social infrastructure and so forth. And in the course of the study, a colleague of mine, Rob Sokolow, who some of you know, and I began thinking about this a little differently from the way the rest of the folks on the study group were thinking. And we suspected something terrible would happen if you drained the Big Cypress Swamp. Namely, there would be salt intrusion into the aquifers that underlie South Africa. Now, modeling aquifers in a place as complicated as South Africa is a big mess. It's a complex system. Sorry, South Florida. Thank you. I rely on my wife a lot. So what did we do? We decided to make a simple back-of-the-envelope type model of South Florida and its hydrology. And the model was very simple. It was a U-tube. You may have remembered from high school chemistry, the U-tube. It's just a glass tube. And so he said, suppose we ignore all the complexity and just think conceptually of a U-tube, that one end of which is sticking out into the Gulf of Mexico, and one edge is in the Big Cypress Swamp. You have fresh water on the land surface, and you have seawater here. And if the fresh water table is above sea level, then you can have an aquifer with fresh water. And it will keep out the salt water because the extra pressure of this above ground level water is enough to drive seawater out of the aquifer and give you nice fresh water for drinking. If you drain the surface water, you can apply something called the 40-to-1 rule, which is every time you lose a foot of swamp water, you're going to raise this boundary 40 feet. The 40-to-1 ratio is a result of the fact that seawater is 2.5% denser than fresh water. So we calculated with this very simple model that really a back-of-the-envelope model, that over 500,000 people in South Florida would lose their drinking water supply. Our finding was publicized. It made the New York Times and a whole lot of other news outlets, and that induced the Nixon administration, remember it was 1969, to cancel plans for the airport. Soon after, the Big Cypress Swamp was preserved in order to protect the water supplies of South Florida. And the lesson for me was very simple models. Idiotically simple YouTube can save the environment, and I was hooked. And that's when my career shifted from physics to environmental science. Of course, that problem was just physics, and we all know physics is simple. How do spherical cows graze in the living world? That was the next topic. So I want to go through several areas of research. The first one rather quickly, and it's the studies that we did through the late 70s and into the 1980s on acid deposition in the western United States, with a particular focus on lakes in the Sierra and the Rocky Mountains. These are very complex systems, and in fact, we were looking at available models of what would happen when acid rain fell in a watershed. What would it do to the lake? And what would it do to the creatures in the lake? And the current widely used model was developed by the Army Corps of Engineers, and literally it had over 150 adjustable parameters, only about 30 of which could be directly measured, and the others were inserted as fitting parameters. And it was appalling, but it was a widely used model. The Electric Power Research Institute used it in justifying all the things that they were doing at the time. So we wanted to look at alternative approaches. And I'm not going to go into great detail on this. I just want to say that we, and I'll tell you who we is in a minute, we developed methods for understanding and integrating across many different areas of science: atmospheric dynamics, geology, soil and water chemistry, toxicology, and zoology. Simplicity emerged from 10 years of research on this, not in a simple formula that somehow magically replaced the complex model, but in a set of crisp and compelling empirical findings that resulted from well-designed observational studies, to use Dick's phrase, and experimental studies. We organized our insights into the behavior of these complex systems in a way that policymakers could understand. The main lessons that we learned from all that work were that severely acidic snow and rain are falling in the western United States, which was not understood at the beginning of the Reagan administration. Highly sensitive mountain lakes and ponds in the Sierra and Rockies. Most of the ponds in the Sierra, most of the lakes, and many of the ones in the Rockies were very sensitive chemically to acidic deposition. We were able to use trace metal fingerprints, this was Charles Blanchard's dissertation research, to identify acid sources, and it turned out the major ones were coal-fired power plants in the Southwest, power plants like Four Corners, and salamanders in the mountain ponds were imperiled by continuing acid deposition. The acid accomplices on all this work, Kathy Tonneson, Charles Blanchard, Asa Bradman, Sammy Yassa, Jim Williams, Harvey Michaels, Andy Gunther, Jim Kirchner, Erica Hoffman. And in the left, you can see, this was the 70s and 80s, you must remember, so of course we were dropping acid in tubs. In this case, the tubs were little plastic containers into which we put salamander eggs, and we put different levels of acidity, and we watched how acid levels affected salamander hatching, and we were able to show that at the pHs that melting acidic snow caused in the ponds in the Colorado Rockies, the salamanders couldn't survive. And indeed, our census data from 10 years of salamander censusing showed that the populations were dying out. So the research and our congressional testimony on acid rain in the West actually had a big influence on the 1990 Clean Air Act provisions. Now, I have to say that one of the reasons we were able to influence policy is that one of our neighbors up in the Rockies was Senator Tim Wirth, a Colorado senator, and he was a close friend. We were college classmates, and he came up and visited the site many times. He learned the science thoroughly. He could present it in the Congress, and it made a big difference to have that contact. I want to talk next about a meadow warming experiment that we started around 1990, and it's also at the Rocky Mountain Biological Lab. We set this thing up with overhead electric heaters to try to simulate what the climate of the year 2050 might look like. And we took 10 experimental plots in a meadow at around 10,000 feet in the Rockies, and we subjected half of them to about 22 watts per square meter of infrared radiation using these white things, which are overhead electric heaters. The effect of those was to cause about 2 degrees Celsius warmer soil, about 20% drier soil, and very importantly, we caused snow to melt several weeks earlier in the heated plots compared to the controls. The heaters advanced snow melt, and you can see that by looking at the difference between the open blue circles and the bottom circles, which look red on my computer. I don't know if they are red. I guess they're red. Those are the heated ones. Notice also, not only did the heated plots cause, lead to earlier snowmelt, but notice that the control plots are trending in the same direction. That's real global warming. We were one of the few places to have 28 years of data in which we could actually study the trends in snowmelt and other variables, which I'll show you. And so we could look in detail not just at what heating does, but what artificial experimental heating does, but also what the real climate warming in the valley is doing. Among the other things that are happening is the vegetation is changing very dramatically. The change is summarized by those two photos at the bottom. On the left, you see Erigeron, a species of daisy, which is disappearing from the heated plots, and sagebrush is growing like gangbusters. So we've changed the species composition. All of the non-woody flowering plants are doing very poorly. Some are at the edge of extinction now in our heated plots. And the shrub, sagebrush, which is abundant at 2,000 feet lower elevation, the sagebrush is doing really well. And as you might expect, you can see on the right, the red is the sagebrush in the heated plots. Even the blue is increasing slightly at the edge of significance. The flowering plants, the non-woody plants, are decreasing faster in the heated plots than in the controls, but they're decreasing in both. This is a dramatic effect which we thought might be leading to other consequences. And one of the things we looked at was the soil carbon, because if the system is losing soil carbon to the atmosphere, that's a feedback to global warming, which will amplify global warming, because the CO2 lost from the carbon lost from the soil is now CO2 in the atmosphere, which is, of course, an important greenhouse gas. So this is what we saw at the end of 10 years, and of course we had to wonder what's going to happen in the next 10, 20, or 100 years. This represents almost a 50% drop in soil carbon, and if that were occurring worldwide in all the soils on Earth, it would be equivalent to doubling the amount of carbon dioxide in the atmosphere. So potentially this could be a huge feedback. Again, we looked at available models, and the ones available at the time had truckloads of parameters, many of which we could not measure, some of which are virtually unmeasurable, and we decided to come up with a simpler approach. So those of you who are ERG students will know what I mean by an ER102 type model. This model was like maybe an advanced homework problem in a course that I used to teach and which Laura Kippers now teaches. The model was very simple. We divided all the carbon into three types: carbon coming from shrubs, from forbs, and from grasses, and we simply did a mass balance on the carbon. As it progresses from the atmosphere, CO2, into growth of the plants die, and the litter from the plants goes into the soil, and then soil carbon decomposes, and back out goes CO2. So we were able to make a simple model. Every parameter in this model could be directly measured. There are only a few. And we compared the output from the model, which had no knobs to twiddle. It was either right or wrong, and it looked sort of like what we saw for the first 10 years. It looked pretty good, so we said, what's it going to look like as you project it out into the future? And when we did that, we went out 100 years. This is a model result. The next 17 years of model prediction look a lot like our data from those next 17 years. So that takes us out to year 27, which was last summer. And the model makes a projection that and if you look at the heated plots, the soil carbon's declining like we saw, but then it's going to recover and eventually overshoot. And this is a consequence of the fact that sagebrush is growing so well, and sagebrush is a plant whose litter, whose dead plant matter, when it goes into the soil, is very long-lived. And so you build up a large pool of carbon slowly in plots that have lots of sagebrush. And we projected out what the control plots would look like under a plausible assumption about the future of the climate in the valley and the future of snowmelt, and using climate model output. And discovered the same thing, except the reversal of the loss of carbon won't occur until about year 60 or 70, and then you'll start to get this recovery. As long as you're below the initial value, you're exerting a positive feedback on climate change. You're exacerbating global warming. When you get to that recovery stage and you have more carbon than you started with, then the system is starting to take carbon out of the atmosphere, and you're helping the world by storing more carbon. So this is what we projected. First, damaging positive feedback to global warming, and then subsequently, 60 years out, reversal with negative feedback. We then asked, well, what would happen if we apply these ideas to other ecosystems? And one of the things we discovered was that if we apply it to conifer forests in the western United States, you get that loss of carbon out for the first 60 years, and then it just continues as a loss of carbon. There's never a recovery phase. So subalpine meadows have first positive feedback, then negative. Conifer forests, you have positive feedback all the way out, which means damage to the climate all the way out. We also tested the predictions of the model on a landscape scale across many different habitat types in the Colorado Rockies, and we found a very good confirmation that the model could accurately predict ambient soil carbon levels. So this was all useful and helpful to know that the model is capable of working in other habitats besides the meadows where we did the experiment. The climate conspirators are all listed here. I'll let you read the names, too many for me to say. But they're a wonderful group of graduate students who were in different ways contributing to this huge effort to understand how climate change is going to affect ecosystems and how ecosystems, as they respond to climate change, will cause feedback to either amplify the climate change or help to cancel it. Now, I want to turn in the last topic to ecology and whole ecosystem ecology. And first of all, nobody could possibly claim that ecosystems are simple. I'm showing here some of the dimensions of complexity in an ecosystem. Up in the upper left is what we call community complexity, which just means the complexity of the mix of species. Below it is phylogenetic complexity, the complexity of the evolutionary history of the ecosystem. Below that is network complexity, a diagram produced by Neo Martinez, who studies food webs and whose work I'll say something about shortly. Then in the bottom center, we have behavioral complexity, biogeochemical complexity, some of which I was talking about in the previous carbon study. Above that, we have, when we dig inside organisms, we have the complexity of metabolic pathways. And then on the top is what I call dynamic complexity, which is the complex ways in which environmental disturbance interact with ecosystems and alter all of the other things, the food webs and the community composition, behavior, and biogeochemistry. Not only is each panel complex, but the panels all influence each other. It's a coupled system, and the coupling, this entire system, which is internally coupled, is coupled to the complex socioeconomic world. So we're dealing with complexity. And yet, the more we look at ecosystems around the world, forests and coral reefs and grasslands, and even the microbiome in your gut, the more we tend to see that nature acts as if there really are laws acting around us. I put that phrase, laws acting around us, in quotes because it's in the last paragraph of Darwin's Origin of the Species, in which he comments on the complexity of an ecosystem and then says, and yet everything is the result of laws acting around us. And evidence for laws is that there really are pervasive patterns. An example, lots of species have small individuals, only a few species have big individuals. Metabolic rates of individuals vary inversely with the abundance of the species that they're in. Many genera and families, these are higher order classifications above the species level, have only a few species, and a few genera and families have lots of species. A few species eat many things, and many species only eat a few things. Now, that's just words, but each one of these has mathematical equations that go with them that pretty accurately describe the patterns that I've described in words. I'm not going to burden you with the mathematical equations, but this is not just hand-waving. In a sense, you can think of our understanding at this point as the Kepler phase of ecology. You remember that after Tycho Brahe gathered all this wonderful data about the orbits of the planets, Kepler looked at all the data and had no idea why the patterns were what they are, but he knew he could see the patterns, ellipses and various relationships relating the radius of the orbit to the periodicity, the period of the planet in its orbit around the sun. In a sense, this is the Kepler phase of ecology. We see patterns and we have mathematical functions that describe them. Now, to go beyond that and to develop ecological theory that will actually predict these patterns and more, I want to go back to about 1790 and tease you with something which I call Laplace's Conundrum. Laplace knew Newton's laws and was busy working out the orbits of the outer planets. Neptune had been inferred from wobbles in other planets' orbits, and he was trying to work out the properties using Newton's law of gravity and determine precisely where these planets were and how heavy, how massive the planets were. And when he started applying Newton's laws to this immensely complicated problem, he ran into an ambiguity. He found there were multiple possible solutions to the information he had at hand. So he had some constraints, but then he had all these alternative possible outcomes, and he wanted to know which was right. So he stewed over that for a while, and at some point, I have no idea how this genius came to think about it this way, but he mapped the problem onto a much, much simpler problem, at least conceptually simpler, and it's an urn, the usual urn that probability analysts like to think about, where you draw red and blue balls from an urn. And he said, suppose you have an urn, and in it you have some unknown number of red balls and some unknown number of blue balls, and you reach in, and let's say you pull out a red ball. Okay, he asked himself, what's the probability that if I reach in and pull out a second one, it'll be red? Now that sounds like an almost impossible problem. And if you're a rigid frequentist in the way you think about probability, it actually is impossible. But he had known from the work of the Reverend Bayes, he knew what Bayes' law was, and he understood the concept of conditional probability, and he filled up 30 pages of notebook with an incredible amount of algebra and came up with an answer, which was actually correct. I'm not going to tell you. I told you I was going to tease you. I won't tell you the answer. You can think about it and email me if you think you know it. But it's an interesting problem because it's at the core of something which 150 years later became a powerful method of inference in science. What happened 140 years later was Claude Shannon developed the concept of information entropy. And then 20 more years later, a physicist named Edwin James said, look, if I take the kind of thinking that Laplace was doing and I combine it with my understanding of information entropy, I don't need 30 pages of notebook to derive the answer to Laplace's conundrum. I can actually do it in about 6 lines on a single piece of paper. Moreover, I can do lots of other things. And what Jaynes did with a concept which I'm going to explain in a second was start to rederive all kinds of important results in physics, like the laws of statistical mechanics and thermodynamics. What do you do? Well, the idea is sometimes called MaxEnt, or maximum entropy. It's not physical entropy, it's information entropy, the very entropy that Claude Shannon introduced to the world in the 1940s. The entropy that Shannon introduced is shown in that equation. It's the sum of p log p, the probability distribution times the log of the distribution. And his measure of entropy is a measure of the lack of structure or detail in the function p of n. His entropy measure is telling you something about how smooth and flat the probability function is. And Jaynes reasoned that, you know, let's figure out what we're trying to do when we do science. We're trying to do inference, and we want to be as least biased as possible. We don't want to introduce extraneous information or results that could influence our answer, but which are not warranted by the evidence. So he said, suppose we put all the evidence we have about a probability distribution into a list of what we'll call the prior information. Then, if we maximize Shannon's information entropy under the constraints of the prior knowledge, we will get the smoothest possible probability distribution that satisfies all the things we know we know. And he said, that's good, because that would be the least biased distribution. It wouldn't assume anything. It would be as smooth and flat as possible, no bumps and valleys that are not warranted by the prior knowledge. Here are 2 distributions. The one on the left has higher information entropy than the one on the right. So if both of those were compatible with your prior knowledge, Edwin Jaynes said, pick the one on the left. Okay. Brilliant work. And since he did this, the work has been used in economics, in ecology by my group of students and myself, in linguistics, and in forensics, and a whole lot of other fields of knowledge where people are seeking the shapes of probability distributions. In each case, these applications involve knowing something at a coarse scale, what you could call the macro scale. For example, in thermodynamics, you might know the pressure and the volume of a cylinder of gas, but you don't know the distribution of the velocities of all the molecules. Applying this maximum entropy procedure of Jaynes, you would predict, it turns out quite accurately, the distribution of molecular velocities. You get the Boltzmann distribution for kinetic energies. In ecology, I will show you that all kinds of predictions flow, and about food webs, about patterns of diversity, about abundance, spatial distributions. And I'm not going to go into the linguistic and economic applications, but they're all interesting. And the main point is an established tool from calculus, something you would learn in an advanced freshman calculus course. It's called the method of Lagrange multipliers, is all you need to derive the least biased inference, the shape of a probability distribution. So we'll use that idea, and we built the maximum entropy theory of ecology, or MEAT for short. Interestingly, MEAT is another word for allocation, and it is a theory of allocation, allocating resources, or energy, other resources to individuals, individuals to species, species to genera, and the distributions across each level in that hierarchy are predicted by MaxEnt. The idea of the theory is something that will work across all the different taxa, plants, insects, birds, the microbes in your gut, spatial scales from little patches to large biomes, habitats, forests, meadows, deserts, tundra, and taxonomic categories, species, genera, families, etc. That was our goal. The results of the theory are written up in a textbook that Oxford Press published in 2011. MEAT and its precursors have a number of partners in crime. They're all listed in the lower left. Just to show you, I'm not going to go into this in detail, but we've done tests of the model of the theory's predictions, 25 distinct habitats, 100,000 species total that we've looked at, and 1 billion individuals. A few of the places where we've carried out tests are shown there. And whether we're looking at size distributions of organisms or abundance distributions of species or something called species area relationships, we see these, that the data tend to follow the predictions of the theory quite nicely. I want to say a little bit more about the graph on the left, the species area slope. A species area relationship tells you, as you census a larger and larger area, how does the number of species you see grow? It's going to increase, but it won't increase in proportion to the area because of all the overlapping. So what will it look like? That function that describes that is called the species area curve. And when people plot species area curves, number of species versus area, you take 50 species area curves around the world and put them all on one graph, and you practically fill the graph paper with dots from all the data. There's no simple pattern, no coherence. It looks like every species area relationship is unique. What the theory said is don't graph it that way. If you want to see the simplicity, plot something different. Take the tangent to the species area curve, the slope, and at each scale, take that slope and plot it on the y-axis, and on the horizontal axis, plot the ratio of the number of individuals to the number of species at that scale. And when you do it, the theory says all the data should follow that solid curve shown on that left-hand graph. And all the dots are data from all the species area relationships around the world that we could get our hands on. And it works remarkably well. So what, you may ask? Well, the theory resolves many important issues in conservation biology. For example, we have what I think are the first reliable predictions for how many species of insects there are in the Amazon, based on using the species area relationships to scale up from small plots where we have very good data. We can predict that there are 18,000 species of trees in the Amazon, which is very close to the current best estimate based on field, ground-based censusing, and 500,000 species of insects, which isn't going to be tested for a long time. It's, but that we do have that prediction. It resolves an important debate about extinction rates under habitat loss. My former student, Justin Kitzes, did a lot of really good work on that topic. It predicts the conditions under which delayed extinctions will occur under habitat loss. That is, things die quickly, but then even 100 years later, you can start to see delayed extinctions. It's called extinction debt, and we're able to use the theory to relate the magnitude of extinction debt to the abundance distribution. It predicts population losses. This was a specific application done in Malaysia with Rebecca Shirley and Justin Kitzes, who estimated population losses if a proposed megadam in Malaysia was constructed. It was published in Ambio, and we're hoping it will have an influence on the actual construction of that dam, which is a hot issue right now in Malaysia. And work of Erica Newman demonstrates how discrepancies from the predictions of the theory are actually a measure of the magnitude of disturbance that the system is undergoing. Systems that are changing rapidly because of recovering from fire or grazing or other human disturbance show very systematic deviations from the theoretical predictions, which means we can use this as an early warning indicator. But now let me get more general. Have we really been locating the simplicity on the other side of complexity, or simply oversimplifying on this side? All of you are probably asking that question. The seemingly complex patterns in nature that ecologists have long tried to predict, with very complex mechanistic models, mind you, and have failed, those patterns that they've been trying to understand are very well described by meat, provided the ecosystem is not undergoing rapid change because of disturbance. Mechanisms inferable from the theory, we can actually back calculate from the theory, and I'll explain how in a minute, are in accord with the intuitions of natural historians, who are the preeminent students of ecological complexity. And finally, failures of meat point to plausible mechanisms. That's how we get to a mechanistic understanding. And there's a beautiful analogy here with statistical mechanics. Thermodynamics leads to the beautiful ideal gas law, which some of you probably learned in high school. Pressure times volume is proportional to temperature. PV equals nRT. And that law works beautifully, except it breaks down at very high pressure. And at high pressure, you have to modify by explicitly introducing into the otherwise purely statistical description of the system. You have to introduce an explicit mechanism, namely dipole-dipole forces, so-called van der Waals forces between molecules. It was the failure of a prediction that led to the understanding of the importance of dipole-dipole forces. And we are finding the same thing. And I don't have time to go into it, maybe in the question period, but there are a number of mechanisms which are now being uncovered from the patterns of violation of the theory under disturbance. One more comment about are we looking on the other side of complexity or oversimplifying on this side? If what we've learned in a very general way is if systems look complicated, maybe that's because you're looking at them incorrectly. And I want to give 3 examples. The one on the lower left we've already done. Species-area relationships look ugly, but if you look at them the way the theory says to look at it, everything looks beautiful and universal. Something similar happens when you look at the growth rates of mammals. From mice to elephants, if you plot the mass of the organism from birth on to death versus time, and you put all the mammals onto one graph, it would fill space. It would look incoherent. But metabolic theory says if you rescale the way you draw that graph, redefine time by scaling it by a function of the mass of the organism as an adult, and replot, all the data should fall on a universal curve. And indeed they do. It's brilliant. And Neo Martinez, Jennifer Dunn, and Rich Williams have applied food web theory, and you can also get at this with MaxEnt, to show that if you look at the distribution of the linkages in a food web, the connections between the species, who eats whom, if you plot the distribution of linkages in all the food webs you can get your hands on one sheet of paper, it looks ugly. But if you rescale according to what food web theory says, then all the data should fall on a universal curve. And to a considerable extent, they do. So we call this scale collapse. It's widely understood and has been used in physics for decades, but it seems to be showing up in ecology as well. How you do the scale collapse, well, you need a theory to tell you how to do it. It's too hard by trial and error. But a good theory predicts scale collapse, which then creates a simple pattern out of what you previously thought was complexity. Okay, part of my self-assignment for this talk was to speculate about where complexity science may be heading. And let me turn to the speculation. Something that has just almost overwhelmed me with its significance is the history of unification in science. And I'm going to look at physics initially at the top. We've got 200 odd years ago, we discovered heat and kinetic energy are one and the same. They're all energy. One can be converted to another. We discovered in the 19th century that electricity and magnetism are in a sense one and the same, the electromagnetic field. We discovered that mass and energy are one and the same, special relativity. We discovered space and time are interconvertible, special relativity. A little later in the century, we discovered that there's a relationship between information and energy. The amount if you have a bit of information, one yes-no decision, processed at temperature T, it takes a minimum of 1 kT of energy to process that bit. That's why your computer heats up. That's why your brain can heat up. Information and energy sort of now starts to link physics with information theory in an intriguing way. And then along came James, who showed thermodynamics and stat mech can be derived from the MaxEnt principle. Recently published work goes way beyond this and shows that we can actually derive quantum mechanics and relativity from MaxEnt. And MaxEnt has provided lots of insight into other fields like economics, neural net firing patterns, protein folding, image resolution, and so forth. So, speculation, pure speculation. Tell me it's wrong. It probably is. But perhaps much more of complex system science is simply least biased inference implemented with MaxEnt. That's where I think the future of complex systems lies, and that this principle, which has proven to be so powerful where it's been used, we haven't even begun to really explore the potential for it. Now, I want to just end with a couple of slides. And nothing to do with what I've said before, except I get the right to do this, since this is my, my sort of semi-swan song. When I grew up, the world looked like that. The years of my childhood, in the early 1940s, victory gardens to help grow food so we could win World War II. My childhood image of nature was that diagram. It's probably from a storybook. And if you look at the map of the world in the upper left, each dot is 1 million people. That's the population when I grew up. It was a third of the human population of the world. It was about a third of what it is today. Today, the population has hugely increased, 3 times what it was when I was a kid. Mountaintops are farmed right up to their summits to provide food for all these people, and we've created mountains of garbage. The threat is not just from population growth, it's not just from per capita consumption, it's from both. And it's also from inequality and maldistribution. All of these forces are working together and creating a situation in which I believe that the future of humanity is imperiled. And not 100 years from now, but sooner. There are really only 2 conceivable futures. What I'm showing in the graph is the number of Earths to minimally meet human needs. And 1 would be the maximum allowed in a long-term sustainable society. And what's happening is we have overshot, and the 2 futures are shown in the dashed lines. In 1, we keep growing. Continued growth in economic throughput, in population, and in inequality. And when we do, we're bound to reach the limits. In a sense, we've already reached them the limits are bound to catch up to us, and we will collapse, and civilization will be over. In the other, we make a transition to a soft landing and a sustainable future. And the biggest task we all have is to steer humanity onto that sustainable course. And I want to conclude with a slide that just says, none of my research, nor any of yours, will matter if we don't reverse human population growth, we continue to act under the illusion that perpetual growth in material and energy throughput is possible and desirable, and we fail to achieve a just and equitable world. And I want to thank, I've got a couple of thanks slides, deep gratitude to all my former graduate students who, I don't think I've ever listed them all in one place before. And many of you are here, and I owe enormous debt to all of you. My career would be nothing to write home about were it not for all of you. Postdocs who have worked with me over the years, and hundreds of undergraduate research assistants who have labored in the field and at the computer. I also want to thank teachers, friends, and colleagues who have encouraged my quest for simplicity on the other side of complexity, provided roadmaps to help me attempt it. The 9 names are listed there. And I want to thank a number of institutions that bred my love of the complexity of nature and fostered my study of it, from my teenage camp that I went to in Vermont, Sage Hill Camp, all the way to ERG today. And then I want to thank all of those who have provided generous support, a number of government agencies and foundations. And lastly, this lecture is dedicated to the memory of Philip Roth. The lecture series is named as the Philip Roth ERG Annual Lecture. He was a wise and caring friend and scholar, and I miss him very, very much. And now it's your turn.
One thing and then
so if you have questions, Megan and Ellis have microphones, so get their attention, and John will take questions from the folks who have microphones.
And please speak loudly. In my old age, I've lost some hearing.
John, thank you for your lecture, but also for your service and your inspiration. You said that ecology is in the Kepler phase. You also referred to the linkages between the ecological subsystems and the social, economic, and ecological system. And you mentioned in several cases that some social sciences, such as economics, were deploying some of these tools. What phase are the social sciences in if ecology is in the Kepler phase?
Well, let me just modify that a little bit, and if I may throw away all pretense of modesty. When I said we're in the Kepler phase, I was saying this is how we understood things when we started this work. I think the MaxEnt theory is slowly getting us a little beyond the Kepler phase, but we'll see. Time will tell. Boy, the social... Let's see, is this thing on now? Yeah. Good. The social sciences, social sciences like economics, I think we actually are able to say things that go beyond Kepler. I think we do have theories. We can use MaxEnt to derive the distribution of incomes in the United States. In fact, let me show you a picture. I was hoping somebody would ask about this. This is a diagram of the percent of income versus, of people versus adjusted gross income on the horizontal axis. So it's the cumulative distribution of income. And MaxEnt predicts a Boltzmann-Gibbs distribution, which works all the way out to about $100,000. And this was in 1997. Beyond that, we get a different distribution. If you go back to 1970, almost the entire distribution was Boltzmann-Gibbs, which is, now think back to what I said about non-disturbed ecosystems satisfy MaxEnt. Disturbance starts to create divergence from MaxEnt predictions. The divergence began around 1984. Guess who became president in 1980 and began altering tax structures in ways that increased inequality? The Pareto distribution is evidence for inequality relative to a purely Boltzmann-Gibbs distribution. So this is beyond Kepler in economics. When you get to sociology and what people call the less quantitative social sciences, it's clear that, to me, that there's some elements that will make it very unlikely to ever develop the kind of theory that we know and love in physics and we hope in ecology and other fields. And that is that people have goals, they have will, and these things, consciousness and goals and will, make it difficult to imagine what a general theory could look like of, say, human behavior or any of the softer, so-called softer. I apologize for using the word, Isha. You're okay with that, good. Makes me skeptical that we'll go beyond, that at best we'll get to Kepler. I'm not even sure, I don't know enough about those fields to even know if we're at the Kepler phase. Yeah, okay. Other questions?
Hey, John, is this, just to build directly on that, as we go into a period of climate change, we hear people, they're sometimes speaking about it in terms of being in a disequilibrium, a state of disequilibrium, or ecological systems in disequilibrium. And I'm just wondering if you would comment on the relationship between what you notice, disturbance, the MaxEnt patterns, and the concepts of equilibrium and disequilibrium systems.
Okay, it's interesting. I was at a conference at Santa Fe Institute 3 weeks ago, and the word equilibrium and disequilibrium were used completely differently by different groups of people. So economists talk about the economic equilibrium. Physicists talk about equilibrium as a state in which there's basically no changes occurring in the quality of the energy in the system. So the climate is always out of equilibrium because very high quality sunlight comes in and low quality heat goes out. So entropy is being produced at a huge rate and the system is out of physical equilibrium. But economists would use the term differently. And I'm not sure how you're using it, but the evidence, we have not yet been able to show that ecosystems disturbed by climate change violate the predictions of the MaxEnt theory. They should, but we don't have enough data yet to be able to do it. From our plots in the Rockies, we just don't have enough information. We need to look at this on a large scale. So since climate change is already affecting the meadows in the Rockies and in the Sierra, and we could, in principle, start to gather abundance distribution data and see whether the small but visible trends in climate that have already occurred are causing the system to behave like a system out of MaxEnt equilibrium. And That's on the agenda of things to do, but we haven't done it yet. Annette?
This is maybe building on this topic a little bit. So, yeah, when you presented maximum entropy, it was very much about an information entropy point of view, but do you view its success as some kind of a indication of how we should think about ecological processes?
Right, do I view what as a success?
The success of maximum entropy theory in describing the patterns we see in nature. Does that, in your mind, give it any indication of how we should think about how ecological processes work? Or?
It's yeah, okay. Is the success of this MaxEnt theory in describing non-disturbed ecosystems reason to think that it's successful? By one definition, yes, it works. The data agree with the predictions, many of which we didn't know what the data said until after we had made the predictions, like that species area prediction. So yeah, it's successful in that sense. Whether it's successful in a much bigger sense, that this is sort of the first step in a general program that could be extended to all ecosystems, all complex systems, is still, the jury's out. I don't know. But I consider the results of the MaxEnt theory to be an indication of success, at least in ecology. Karina.
So I started recently kind of reading more on this concept of regenerative capitalism.
Which capitalism?
Regenerative capitalism.
Regenerative capitalism.
Which is a terrible name for it, actually, because it's introduced by the concept that capitalism is unsustainable, but we're going to talk about this thing called regenerative capitalism, which is essentially a measure of what is economically sustainable. So the naming is weird, but the concept that's being proposed here is that systems theory, not well defined, is generally applicable to ecosystems, but that those same underlying principles describe social systems, economic systems, and that the metrics of health that we should be using for an economy are measures of system health. So is MaxEnt, I mean, to me, I look at your data and I was saying, the failure that is describing this thing no longer fitting the theory. Maybe those are the metrics that we're looking for sustainability writ large.
That's right. Yes, that's consistent with the idea that the failure of simple theory describing ordinary situations, what might be called equilibrium or steady state, the failure of theory to describe a system is an indication that the system is going haywire in some direction due to some cause. And sometimes you can begin to understand from the pattern of failure what the cause is. And that, I think, is a very fruitful way to go about making advances here.
Very nice.
So I think I also have a question about the case when a disturbance, when you're looking at a disturbed system. Do you, because we also want to predict those and how a disturbance affects that. Do you think that MaxEnt can help us there, or do we need a completely different approach?
Did I plant this question for you?
No.
As evidence that I'm not really retired, I just got an NSF grant for 3 years to
really did not know that.
To answer that exact question. How do we extend the theory to actually account for and describe the nature of the response to disturbance? How do we find the dipole-dipole interactions in an ecosystem that are starting to screw up the predictions? How do we take our understood as, maybe sometimes we know what's causing the disturbance. There's a very well-studied forest in Panama called Barrow, Colorado Island Smithsonian plot. And in it, something very interesting is happening. Where undisturbed tropical forest plots look just like what theory says they should look like, that one is deviating from theory. And that plot was disturbed about 80 years ago when the Panama Canal was built and Lake Gatun was created as part of the canal. The Lake Gatun created all these islands, which were the mountain peaks that didn't flood. And Barrow, Colorado Island is one of these little peaks, one of these little islands in the middle of this giant lake. And the result of creating the lake is you've isolated that plot from the immigrant pool from the surrounding forest. And the result of that has been a very systematic pattern in the way in which the patterns at BCI deviate from the MaxEnt predictions. Non-disturbed tropical forest plots look like MaxEnt says they should look. BCI looks different. And we know the mechanism. It's the shutting off of the immigration pool, the pool of migrants. It's doing what Donald Trump's trying to do. And what happens when you do that, we now know empirically, we can see it. So that's going to be the first test of this theory we're building. I call it Dynameat because it's a dynamic extension of meat. And we're just got a grant and I'll be hiring a postdoc and a grad student to work on this.
So you might try to predict what Donald Trump is doing?
Well, actually, it might be easy because there's no will, there's no goal, there's no... maybe a purely statistical model. Random neural net would probably do it better than any theory.
There's clearly a case of a disturbance, though.
Yeah.
Thanks, John. I have a very related question, and just that it seems to me that at least in some cases, disturbance isn't the exception but the rule. For example, fire-dependent ecosystems, or maybe in boom-bust cycles in the economy. And so, I guess, is there a way to extend MaxEnt to think about those? Should we be thinking about those systems differently from systems that are where equilibrium is the norm and disturbance is the exception? Is there sort of should you be thinking about the world as two different types of systems or together?
There's going to be a continuum from as undisturbed as conceivable and compartmentalized. Right? There's disturbance is not a yes/no thing. So the question becomes, what is the domain where this newly developed theory we're working on, if we get it to work, then will work? And what does it say about behavior under disturbance? And then, in a sense, the original theory will be the limiting case of dynamic where you turn off the disturbances, where you turn back the immigration, and whatever. So along that, I don't know what he did. What happened?
He gave you your voice.
Oh, okay. So, the answer is that's exactly what we hope to do. But I don't think it's going to be it's in this bucket or it's in that bucket. It's going to slosh from mostly in that bucket to mostly in that bucket, and we'll see. But that's still to be worked on. Neo. I was waiting for Neo to answer.
Took me a while to figure one out. I was wondering, do you have, well, first of all, thanks for a wonderful overview of brilliant careers that's keeping on going. I love that. And I wanted to see get you to describe the connection between the models in the earlier part of your talk. You have the YouTube model and the soil carbon model and the model of acidity, which are, you know, very simple, elegant, mechanistic models with pretty immediate policy implications. And then in the later talk, you have a more, shall we call it, sophisticated theoretical model where the mechanisms are unclear and the impacts, the immediate policy impacts are less clear. So describe the connection between those two.
First of all, there's an important distinction between a model and theory. And in the last part of the talk, the MaxEnt theory, we call that a theory because it predicts so many things so comprehensively from a very small number of inputs. We tried to come up with a model that could explain all those Keplerian patterns in ecology. And you have this beautiful niche model that does a good job with food webs. We could not come up with something comparable that could explain, you know, put it all together, or even one by one. A good model of the species-area relationship simply doesn't exist. We tried. We came up with Ann Kinsick and Jess Green and Annette Osling and others worked on different attempts at coming up with models to do just a small number of things, but with some very specific assumptions and not MaxEnt. And we just failed. We failed time after time. So that led us to think maybe there's a more general approach to theory building. And then I came across all this beautiful work in statistical mechanics, and I realized that this could be relevant in ecology. The models that we use to do things, the YouTube model and the rolling quarter model, are perfectly appropriate. They're wonderful. They're powerful ways to get insight into some specific situation. But they don't provide the comprehensive theoretical perspective. The MaxEnt can predict food webs. It can predict the structure of taxonomic trees, abundance distributions, mass abundance relationships, and so forth. That's a lot to do, and no simple, I don't think any simple mechanistic model could do it. The problem in ecology is that you have this vast list of mechanisms, the traits that species have, different ways in which they interact with each other. I've only listed a small subset of all the ones that ecologists have studied and think about. You have this vast list of potentially important mechanisms. And then you have multiple abiotic factors that could exert an influence, stochastic or inherently statistical behavior, historical contingency, ambiguous system boundaries, difficulty conducting large-scale controlled experiments, and difficulty isolating particular stresses. All of that makes ecology extremely resilient to simple modeling. And that's why I think it's almost, in a sense, because of the complexity of ways in which species can achieve some sort of a balance on the fitness landscape. Right? If you have an ecosystem in more or less of a steady state, those species have all figured out a way to be there. And each has figured out, using different combinations of these mechanisms, how to survive and coexist. And it's because there are so many processes that we can ignore them and instead turn to a more inferential statistical approach. That's my sense about why this works and why other approaches don't.
So thank you, John. It was really terrific. I would like to ask a question which is not about ecology per se, but about science broadly. If, like E.O. Wilson, today you were to write your letter to a young scientist, you have, this room is full of your students. Many of them themselves have students, right? We are still producing students. Tell us two things that you would tell your young scientist.
I'm glad you said two, because as you were asking, I was thinking two things.
I just want to.
The first thing is, if you're going to go into any of the natural sciences, especially things like ecology or biology, the most important thing you can do is go out and walk in the woods and swim in the reefs and walk in the desert and see, observe, listen, smell, and absorb as much of the complexity as you can. You can't get to the other side of complexity until you've been on this side and burrowed through it. If you try to skirt around it, you'll do what Einstein warned us about in his quote. So get to know the world. Get to love the world. That's really important. I'm just finished reading the biography of Alexander von Humboldt by Andrea Wolf. It's a brilliant book, and it's so inspiring to see how his voyage to South America taught him so much, because he listened, he smelled, he felt, he did everything sensual that he could with nature, and went on from there to develop a very systems-level approach to thinking about ecology. So that's number one. Number two will sound almost contradictory, but it's not. I was appalled very recently by a book that one of my heroes, actually, Wilson at Harvard, wrote, the famous ecologist, advice to a young scientist. And he said, I thought it was a good book up until I came to the point where he said, don't bother learning math. You can always go to somebody in the math department and ask them. And I said, no, that's not what you should be telling people. Students need more math than they tend to get, especially in fields like ecology and biology. But, you know, physicists get enough math. But in many, many other fields, they're not learning enough of what modern mathematics has to teach us. And it's not just modern, it's 18th century mathematics. So learn math and love nature.
What a perfectly fitting conclusion to end on. So thank you so much, John. Before everybody disperses, I just wanted to make a couple of quick announcements, or really invitations. So first, I wanted to let those of you who aren't already aware know that on Saturday, you are welcome to attend the John Harte retrospective panels that will be held at the UC Berkeley Faculty Club. There's information that was handed out with the program when you came in the door, so we hope you can make it. You're all very welcome, whether you were a former student of John's or not. And then also for ERGs and affiliates and ESPM folks, friends of ERG, we are, subsequent to this event here, holding an informal gathering at Anthony Hall, which is just across the way from Barrows Hall. So if you don't know where to go, you can either follow the crowd or ask somebody at the door here who can direct you how to get there. Excuse me? Look for the pelican, right? You got to get close to find the pelican, though, as big as the pelican is. Okay, so that's it, and have a good evening, everyone. Thank you so much for being here.
Thank you.